All right, let's start. Welcome everyone. Today we are going to be doing exercises regarding exponents geared towards anyone preparing for the GMAT, specifically for the quant reasoning portion of the GMAT. This could also be applicable, of course, to the EA, and if you are also doing the GRE, this might be helpful as well. But of course, this is optimized for GMAT test takers. Great. So I'm going to start off talking a bit about me. I've been coaching the GMAT for over 6 years, coached more than 250 MBA hopefuls. I used to work as a GMAT director in an institute that provided GMAT and admissions consulting services. I have 40 plus 5-star reviews on Leland alone. In regards to my academic endeavors, I completed my MBA at the University of Chicago Booth. I got a merit-based scholarship as well as offers from other top programs. At Booth, I was selected as Argentina country captain, working with Booth's admissions committee and team. I consider myself really good at admissions consulting as well. Had great results. As for my professional endeavors, during the MBA process, I got 4 consulting offers before joining Booth. Signed with BCG. I was a mentor at Booth's Consulting Club, and I'm also a great resource if you need any mentorship for consulting interview prep. Great, so let's talk a bit about today's workshop. We, of course, are going to go over exercises regarding exponents. You will be given 3 to 5 minutes to do each exercise, and then I will explain how to do the exercise step by step and how I think it's best to approach that particular exercise. I would please ask you to not use your microphones, to keep it muted throughout the session until the very end, where I will open up some Q&A. You're going to notice on the left-hand side, on the top left corner around here, you're going to have an ID for each exercise. If you have a particular question you would like to ask regarding any exercise we go over today, more than happy to help you out via message through Leland. Not the chat right here, more like through my profile. You can access my profile with this QR code right here. And yeah, I hope you guys enjoy what we have in store for you. Let's do our first exercise. You have 4 minutes to do this. All right, time is up. I hope you had time to attempt this exercise. The important thing is that you tried to do it. Now, I would ask you to put down your pencil or pen and just absorb this explanation. All right, so this is the operation we must do. 10 to the sixth minus 10 to the third times 0.00038. Now I want to focus on this decimal right here first. So the decimal has 1, 2, 3, 4, 5 spaces to the right of the decimal point. And so we can put it into fraction form. We would have 38 over 1 followed by 5 zeros. So essentially what we have is 38 times 10 to the minus 5. Because if we have 38 over 10 to the 5, that's basically 38 times 10 to the minus 5. Great. Now let's look at this part of the operation. 10 to the sixth minus 10 to the third. Now, what we want to do is make the two terms look as similar as possible. Now, using the exponent rules, 10 to the sixth is the same as 10 to the 3 plus 3, which is essentially 10 to the third times 10 to the third. That's another way of viewing 10 to the sixth. And we have minus 10 to the third, of course. We can factor out the common term, 10 to the third. And what we have is 10 to the third times 10 to the third minus 1, which is approximately 10 to the third. Essentially, 10 to the third is 1,000 minus 1, 999. But when we look at the prompt, it says approximately the value of. So we can round it to 10 to the third, and we have 10 to the sixth. 10 to the sixth times 38 times 10 to the minus 5. Now we see two terms are very similar. 10 to the sixth times 10 to the minus 5. And using exponents rules, we basically add them. So we have 6 plus negative 5, which is equivalent to 6 minus 5. And we're left with 10 times 38, which gives us 380. Now, approaching exercises that deal with a lot of decimal points, when you're dealing with approximately the value of, you want to make your life easy on the GMAT, considering that you don't have a calculator for the QR section. So you have to think of ways to be very organized and optimize your efforts when approaching these mathematical operations. Great. Let's go on to our next exercise. You have 4.5 minutes. All right, time is up. Hopefully you had the chance to attempt this exercise, perhaps even completed it. That's great. Let's put our pens or pencils down and pay attention to this solution, this particular approach. So this is the operation we have to complete, and I want to be organized very similar to the previous exercise. So let's focus on this term right here, 0.0048. This is equivalent to 48 over 1 followed by 4 zeros, because we have 4 spots to the right of the decimal point. So 48 over 10,000 is equivalent to 48 over 10 to the fourth, which is equivalent to 48 times 10 to the minus 4. We do the same process for this term, 0.36. 0.36 is equivalent to 36 over 100, which is equivalent to 36 over 10 squared, equivalent to 36 times 10 to the minus 2. This is what we call scientific notation. It's making the terms look as similar as possible to be able to do this division without a calculator. All right, let's look at 0.02. This is equivalent to 2 over 100, equivalent to 2 over 10 squared, and therefore 2 times 10 to the minus 2. Great, this term, 0.00003, is of course 3 over 1 followed by 5 zeros, which gives us 3 times 10 to the minus 5. 1.2 is equivalent to 12 over 10, and therefore 12 times 10 to the minus 1. So now we basically made these terms that had different amounts of spots to the right of the decimal point. We made it look very similar. It's all about organization. So now let's look at the numerator. We see that we have 10 to the something in both terms. We can use the exponents law, and basically when we're multiplying 10 to the minus 4 to 10 to the minus 2, we add those powers. So we have 48 times 36 times 10 to the minus 4 plus minus 2, which gives us 48 times 36 times 10 to the minus 6. And we do the same process for the denominator. We see that we have the product of something to 10 to the power of something in each term. So we can group up using exponents values. And we have 10 to the minus 2 plus minus 5 plus minus 1, of course, times 12 times 3 times 2, which gives us a very neat denominator of 2 times 3 times 12 times 10 to the minus 8. Now we can multiply the fraction by 1 and respect the value of the fraction itself. And we are going to multiply by 1 in a way to make our lives easy. Essentially, multiplying by top and bottom 10 to the 8th. That way, the purpose is to remove this 10 to the minus 8. So what we have essentially is on top 48 times 36 times 10 to the minus 6 plus 8. And on bottom, we have 2 times 3 times 12 times 10 to the minus 8 plus 8, which of course gives us a numerator of 48 times 36 times 10 squared, and on bottom, 2 times 3 times 12 times 1. Now the 3 times 12 on bottom cancels out the 36 on top. And when we divide 48 by 2, we have 24. So essentially, our denominator is completely canceled out. It's equal to 1. And on top, we have 24 times 10 squared, which gives us 2,400, and E is our answer. Great. So what's really important to gain from this exercise is you're applying the same principles we used in the first exercise of organization, being methodological, thinking, how can I break up complex terms into more simpler and more manageable pieces? That is something you can apply to any question on the GMAT. That is what your mind should always think about, not what operation I have to do or what strategy should I use. The overarching goal of the GMAT is to use your reasoning abilities to make your life easy. And then you'll be amazed of what comes to your head and what you can accomplish. Great. So let's look at the next exercise. You have 4 minutes. All right, time is up. Hope you had a nice time approaching this exercise. Let's see if we can do this in a simple and elegant fashion without a calculator. I'm sure there's a way. So once again, you must understand that you do not have a calculator for the QR section. And the GMAT knows this. So of course, the GMAT's giving you exercises that you can definitely do in under 2 minutes without a calculator. It's just about you finding a way through your reasoning ability to do that. The math should not be hard. If you're doing hard math, you're not approaching it in optimal GMAT fashion. So let's look at this exercise. Now, I can't do 10 to the 130 minus 32 without a calculator. It's a huge, huge number. But I can do 10 squared minus 32. That equals 68. And you might be asking, why are we doing this operation? Well, because if I can't do 10 to the 130 minus 32 without a calculator, and the test knows that I don't have a calculator, then of course I should be able to solve this in a simpler way. So instead of thinking or overthinking, just put out onto the paper what you can do. We can do 10 squared minus 32. That is 68. Gives us a sum of digits, 6 plus 8. We can do 10 cubed minus 32. That is 968. Sum of digits, 9 plus 6 plus 8. We can do 10 to the 4th minus 32, which gives us 9968. Sum of digits, 9 times 2 plus 6 plus 8. 10 to the 5th minus 32 is 99968. And I'm not speaking German, I'm just repeating nines. And that is where the pattern should start being evident for you. There's a pattern coming. Yes. So 10 to the 6th minus 32 is just another 9. Sum of digits, 9 times 4 plus 6 plus 8. So essentially, the pattern that comes from just doing what you can without a calculator, we have, if we have 10 to the n, and we don't know what n is, minus 32, essentially what we have is 9, n minus 2 times, followed by a 6, followed by an 8. This is the case if n is an integer, of course. And so the sum of the digits is essentially 9 times n minus 2 plus 6 plus 8. All we have to do now is plug in 130 for n. And we're left with a sum of digits of 9 times 128 plus 14, which gives us 1,166. That is our answer. So the important thing when you're tackling the QR section of the GMAT is to not get intimidated by these humongous terms or numbers. Don't get into panic mode. The important thing on the QR is not your math ability, it is your ability to use simple math as a vehicle to show your reasoning abilities. You can see that the math was not difficult. What was difficult is perhaps getting to the math we must do, basically finding that pattern through reasoning aptitudes. Great. Let's go on to our next exercise. You have 5 minutes. All right, time is up. I hope you had time to attempt this exercise, perhaps complete it. The important thing is that you try, right? Let's see how we can approach this. So this is the operation we must solve. Looks like a lot of stuff is going on, definitely. We have on the left-hand side, x squared plus y times y cubed plus 2x. And on the right-hand side, we see, of course, plus y to the fourth plus x times x plus 3y. Now, you must know that this is not a math test. This is a quant reasoning section of a reasoning test. So the reasoning comes into play in this particular exercise when you're dealing with such a convoluted or complex operation. How can you maintain order? How can you maintain organization? How can you make your life easy? So we are not going to input the values for x and y respectively. First, we are going to clean this up as much as possible. I'll show you what I mean. Let's focus on the left-hand side. We have x squared plus y times y cubed plus 2x, which is equivalent to x squared plus y to the fourth plus 2xy. All we did was distribute the y to both terms in the parentheses. Great, this looks a bit more manageable. Now let's do the same process for the right-hand side. What we have is y to the fourth plus x times x plus 3y. This is equivalent to y to the fourth plus x squared plus 3xy. All we did was distribute x to both of the terms within the parentheses. And now we're left with this, which we can also clean up a bit. Basically, x squared plus y to the fourth plus 2xy plus y to the fourth plus x squared plus 3xy is equivalent to 2x squared plus 2y to the fourth plus 5xy. So essentially, we made our lives a bit easier, right? We had this very nasty term or operation right here, and we're left with this more cleaned up version. And now we can apply or input the values for each variable respectively. So y equals 4. Let's input this into the operation we have right here. Basically, 2x squared plus 2 to the times y to the fourth plus 5xy becomes 2x squared plus 2 times 4 to the fourth plus 5x times 4. Now, when we look at this term right here, 2 times 4 to the fourth, basically 2 times 4 to the fourth is equivalent to 2 times 2 squared to the fourth. And using exponent rules, when we have a term like this that's elevated, what we do is we multiply the powers. So 2 squared to the fourth becomes 2 squared times 4, which is 2 to the eighth. Now, the easiest way to do this operation is to literally just write it out. We have 2 to the 1, 2. We double dot, 2 squared 4, 2 cubed 8, 2 to the fourth 16, 2 to the fifth 32, 2 to the sixth 64, 2 to the seventh 128, and 2 to the eighth is 256. So we have 2 times 256, 512. 5x times 4 becomes 20x. All right, so yeah, this is looking a lot more manageable. Essentially, what we have now is 2x squared plus 512 plus 20x. And now we can input the value for x into this operation. We're left with 2 times square root 3 minus 2 squared plus 20 parentheses square root 3 minus 2 plus 512. And now let's just use the exponent rules. When we square a term such as this, for example, a minus b, what we have is the first term squared plus the second term squared minus 2 times the first times the second term. So we have square root 3 squared plus 2 squared minus 2 times parentheses square root 3 times 2, which gives us 3 plus 4 minus 4 times square root 3. We input this over here. Basically, we're left with 7 minus 4 square root 3. And now we can look at the term 2 times 7 minus 4 square root 3. When we distribute the 2, we're left with 14 minus 8 square root 3. And we do the distributive property right here. 20 times square root 3 minus 2 is equivalent to 20 times square root 3 minus 40. And now we see similar terms. We have minus 8 square root 3 plus 20 times square root 3, which gives us 12 square root 3. When we look at 14 minus 40 plus 512, we have 486. So by inputting the value of x into this operation, we are left with 486 plus 12 times square root 3. And now you might think, okay, we have square root 3. I don't have a calculator. How can I do this? There must be a way to solve this without a calculator. You have to always know that. So you don't think about what you don't know. Think about what you do know. We know that square root 3 must be greater than square root 1. And we know that square root 4 must be greater than square root 3. So we know that 2 must be greater than square root 3, which must be greater than 1. And if I look at 12 square root 3, I can multiply the other terms. So if we have 2 is greater than square root 3 greater than 1, that means that 12 square root 3 must be less than 12 times 2, yet greater than 12 times 1. And therefore, 12 square root 3 must be less than 24, yet greater than 12. And then we see 486 plus 12 square root 3. We can add 486 on both sides. And we're left with 486 plus 12 times square root 3 must be less than 510, yet greater than 498. The only answer choice that complies with this range is B, 507. So what's important to really gain from this exercise is not expecting yourself to have to do mathematical operations from the very beginning. You have to give yourself time to think about a way that you can optimally approach this. Don't input the values for the variables until you simplify this complex operation as much as possible. And when you're given a difficult term, such as square root 3, you must know that the GMAT knows you don't have a calculator, so there must be a way to use your reasoning abilities to solve this. So you think about, what could square root 3 be? and square root 3 could be anywhere between 2 and 1. And with that, trust that it might get you somewhere and that it can give you a chance to get this correct. And indeed, it does. Also know that the GMAT is not a fill-in-the-blank test. It's a multiple choice test. So the right answer is right here. You just have to choose it. So that allows you to also use this type of reasoning to attain the correct answer choice. Great. That was fun, right? Let's go on to the next one. You have 5 minutes. All right, time is up. I was inspired to make this exercise while having breakfast. I was watching this YouTube video on intergalactic measurements and how it's just like huge, like to a point where we can't even fathom how huge the universe and infinite it is. And yeah, I wanted to do this with you guys on a Saturday. No better thing to do than to think about an intergalactic map and how far Andromeda would be. Okay, right, so let's try to do this together. Definitely a lot of stuff going on, a lot of big numbers. So of course, we're going to make our lives as easy as possible. So our goal is to find the approximate distance to Andromeda on the map with the scale that we're given, that we have to calculate. And we can assign that approximate value as X kilometers. So yes, it's going to be a huge map, huge intergalactic map spanning kilometers to be able to show the infinite universe. Great. So we want to make our lives easy by being very organized and try to make each term as similar as possible to other terms, because essentially we have to compare the distance to Andromeda with that of the sun. So we know that the distance to Andromeda in actuality, not on the map, but in actuality, is approximately 3.05 times 10 to the 24th kilometers. Huge number. And we can approximate this. All right, we want to make our lives easy. The GMAT uses the word approximate for us to use that to our benefit and to make our lives easy. So the distance to Andromeda is approximately 3 times 10 to the 24th kilometer. And the distance to the sun is approximately 147 million kilometers. And we can approximate this to 150 million kilometers. And you should always have in the back of your head, all right, so I rounded the distance to Andromeda a bit lower than it actually is, and I'm making the distance to the sun a bit more than it is. So some way, perhaps you're balancing it out. That's great. Just know that what you're doing is completely fine and is encouraged for these types of exercises. Now, we want to make the terms look as similar as possible. So if we have the distance to Andromeda in scientific notation, then we should do the same for the distance to the sun. So in scientific notation, 150 million is 150 times 10 to the 6th kilometer. Now, we really want to make it look like this as much as possible. So we can pass a 10 over here. So essentially what we did is we divide 150 by 10 and we multiply this by 10. So we balance it out. And 15 times 10 to the 7th is equivalent to 1.5 times 10 to the 8th. And now they look pretty similar. But let's make Andromeda's distance look similar to the sun's distance now. So bear with me. We have Andromeda's distance as 3 times 10 to the 24th kilometer, which is equivalent to 2 times 1.5 times 10 to the 24th. And I do this, why? Well, to make this distance look as similar as possible as this distance. And we continue. So I see that the sun's distance is 1.5 times 10 to the 8th. Well, I can get that here. If I separate 10 to the 24th into 10 to the 16th times 10 to the 8th, then bam, I have something that looks very similar to the distance to the sun. And now I can put Andromeda's distance in terms of the sun's distance, because we see a 1.5 times 10 to the 8th kilometer in both values. So essentially, Andromeda's distance is approximately 2 times 10 to the 16th times the distance to the sun. Great. Now we can look at the map, the huge map, the entire universe. All right. So we know that on this map, the distance to the sun is 0.5 centimeters. Now we know that the distance to Andromeda is approximately 2 times 10 to the 16th times the distance to the sun. Now the distance to the sun has been scaled down in proportion. In proportion, everything should maintain and be respected. So even though we're looking at the map and not the actual distance, the distance to Andromeda should still be approximately 2 times 10 to the 16th, whatever the distance to the sun is. So now we can input what the distance to the sun is, and we get the distance to Andromeda on the map is 2 times 10 to the 16th times 0.5 centimeters. Now we can make our lives a bit easier by multiplying 2 times 0.5 centimeters, and we're given 10 to the 16th times 1 centimeter. Awesome. Just making our lives easy. So the distance to Andromeda on the map is approximately 10 to the 16th centimeters. But we're being asked in kilometers. So we must be able to translate this into kilometers. Let's be organized. It's getting us to good results so far. Let's continue to be organized. So 1 kilometer is 1,000 meters. So 1 kilometer is 10 to the 3 meters. We know that 1 meter is 100 centimeters. So 1 meter is 10 to the 2 centimeters. Now we can input the value for 1 meter in terms of centimeters. So 1 kilometer is equivalent to 10 to the 3 times 10 to the 2 centimeters, which of course gives us 10 to the 5 centimeters. Now we input what kilometers are in terms of centimeters. So if 1 kilometer is 10 to the 5th centimeters, that means that 10 to the minus 5 kilometers is equivalent to 1 centimeter, right? You pass it over here as a minus expression. And now we can input the value of kilometers in terms of centimeters into this. So the distance to Andromeda on the map is approximately 10 to the 16th times 10 to the minus 5 kilometers, which gives us approximately 10 to 11 kilometers. Now we look at our answer choices, and we want to translate them into scientific notation to see which is 10 to the 11. So A is equivalent to 10 to the 9, B is equivalent to 10 to the 10, and C is equivalent to, yes, 10 to the 11, and that is our answer. What we can get from this exercise is that the math itself is not particularly, sorry about that, it's not difficult. It's more difficult to pronounce particularly, right? Okay, so the math is not difficult. What is difficult is getting to the math one has to do. It is being organized. It is trying to make your life as easy as possible. It is to reason using simple math. Great, let's go on to our next exercise. Pretty similar, so I hope you have a better time attempting this exercise, you have 5 minutes. All right, time is up. Oh, that's a old universe. That's an old Mars as well. There are a lot of minutes in a year. And of course, it's always useful to know how old Mars is as a percentage of the universe. It's a great dinner table chat, right? Okay, so let's see how we can approach this exercise. So we're being asked approximately how old is Mars as a percentage of the universe's age. So we're looking for a proportion of Mars in terms of the universe. We put that into a percentage form, bam, we have the answer. Of course, we want to appreciate that the GMAT is allowing us to round and approximate values, basically allowing us to make our lives easy. Great. So we're looking for Mars over the universe, and we are just going to input the values that we are told in the prompt and make our lives easy by approximating Mars to 2.37 times 10 to the 15th minutes. The reason why I approximated Mars to 2.37 is that the universe is given to us in 1.37, 2 decimal points or 2 spots after the decimal point. Let's do the same for Mars. Great. Now we input the values for Mars and universe, and we're given 2.37 times 10 to the 15th minutes divided by 1.37 times 10 to the 10th year. Great. We're trying to find a proportion. We want to make the values as similar as possible, essentially using the same unit of measurement. The GMAT is giving us how many minutes are in a year, and so we will translate everything into either years or minutes. So we know the universe is 1.37 times 10 to the 10th years old. We can input the value for minutes in a single year, and therefore the universe is 1.37 times 10 to the 10th times 5.25 times 10 to the 5th minute. And so if we use exponent rules, we can multiply the 10 to the 10th times 10 to the 5th essentially by adding the two powers. So we have 1.37 times 10 to the 10 plus 5, which is 10 to the 15th, times 5.25. This is how old the universe is in minutes. Now, to make our lives easier, let's approximate 1.37 to 1.33. The reason why I do this is because using fractions for these operations makes our lives a lot easier given the fact that we don't have a calculator. So 1.33 is essentially 4/3. Great. And let's use the same logic for 5.25. 5.25 is essentially 5 plus 1/4, because 0.25 is 1/4. And we can now multiply 4/3 using the distributive property. And we're left with 4 times 5 over 3 plus 4 over 3 times 4, of course, times 10 to the 15th minute. But let's focus on this, on these two terms, this addition. We have 20 over 3 plus 4 over 12. 4 over 12 is 1/3. So when we add these two fractions, we have 21 over 3, which is 7 So the universe is approximately 7 times 10 to the 15th minutes old. Great. So we look back at our fraction, Mars over the universe, and we can cancel out the similar term or the identical term on top and bottom. And we're left with 2.37 over 7, which is approximately 1/3. 1/3 is 33%. And D is our answer. So the math, if you're organized and you're trying to make your life as easy as possible, the math is not hard. If you're doing hard math, it is because you're not doing it the GMAT way. Great. Let's go on to our next exercise. You have 4 minutes. All right, time is up. Let's see how we can approach this. So we have 4 to the x minus 4 to the x minus 2 is equal to 5 to the 3 plus 5 to the 2. And we, of course, are looking for the value of 4 to the x. You must understand that x doesn't necessarily need to be an integer, and therefore it is possible for 4 to the x minus 4 to the x minus 2 to equal a multiple of 5. And also keep in mind that we don't need to calculate the value for x. Rather, we are looking for the value of 4 to the x. Great. So let's first simplify the equation by solving what we can definitely do, which is 5 cubed plus 5 squared. Now 5 cubed plus 5 squared is equivalent to 125 plus 25, which gives us 150. Great. So we're told that 4 to the x minus 4 to the x minus 2 equals 150. And I really want you to think what you can do using all the resources at your disposal. And those resources include the answer choices. And that's why there are actually two ways I would approach this problem. Way one, back solving, essentially using the answer choices to our benefits. And the second way, the traditional algebraic way. We are first going to do the back solving way. So once again, let me highlight 4 to the x minus 4 to the x minus 2 must equal 150. We know that 4 to the x minus 2 is essentially 4 to the x divided by 4 to the 2. 4 to the 2 is 16. So let me highlight 4 to the x minus 2 equals 4 to the x divided by 16. And now we can use the answer choices. We know the answer choices represent 4 to the x. So we can make a table that has a column for each answer choice, a column for the value of 4 to the x, column for 4 to the x minus 2, and then what we are going to do is essentially subtract this value with this and ask ourselves, does it equal 150? If it does, that's our correct answer choice. All right, so we can quickly input the values for 4 to the x given the answer choices. And now we can calculate 4 to the x minus 2 using this equation. For instance, an answer choice A, when 4 to the x is 8, 4 to the x minus 2 is not an integer. And therefore, 8 minus something that's not an integer can never be an integer. It's definitely not 150. So we can eliminate answer choice A. In the case of B, when we have 4 to the x is 16, 4 to the x minus 2 is 1. 16 minus 1 is not 150. Let's look at answer choice C. 4 to the x is 64, and therefore 4 to the x minus 2 is 4. 64 minus 4 is not 150. D, 4 to the x is 160. That tells us that 4 to the x minus 2 is 10. And yes, 160 minus 10 is 150. And D is our answer. Now, I prefer this method to approach these types of exercises because it is making your life extremely easy. You do not have to fill in the blank on the GMAT. You have to choose the right answer choice, meaning the right answer choice is in front of you. You just have to choose it. Let's look at the traditional way. So we go back and we rewind a bit to 4 to the x minus 4 to the x minus 2 equals 150. Now I want to look at 4 to the x. 4 to the x is equal to 4 to the x minus 2, 4 squared. Great. So we have that. And therefore, 4 to the x is equivalent to 4 to the x minus 2 times 16. Now let's look at this term, 4 to the x minus 4 to the x minus 2. So we know the value of 4 to the x in terms of 4 to the x minus 2. Essentially, 4 to the x is 4 to the x minus 2 times 16. And of course, we have minus 4 to the x minus 2. We can factor out the 4 to the x minus 2. So we have 4 to the x minus 2 times 16 minus 1, which gives us 4 to the x minus 2 times 15. Now, when we look at this operation, 4 to the x minus 2 times 15 equals 150. We have that 4 to the x minus 2 is equivalent to 150 over 10. Sorry, 15, not 10. So 150 divided by 15. So we have 4 to the x minus 2 equals 10. And if we have 4 to the x minus 2 equals 10, we input it back here. So 4 to the x equals 10 times 16, or 160. That is our answer. So both ways are definitely appropriate ways to approach this particular exercise. I personally like the back solving method. And a question I have from my students sometimes is, how do I know when to use the answer choices? How do I know when to back solve? And I tell them, if your goal is to go into an exercise thinking, how can I make my life easy? Then you will give yourself the time and space to breathe and look at everything you have at your disposal. So that's the point when you will decide if it's better for you to use back solving or traditional algebraic methodologies. Great. Let's go on. No, let's take a 3-minute break. 3 minutes. We'll be back at 30. What I would like you to do, if you're finding this workshop useful, is when you leave this workshop, we're not done yet. When you do leave, please put a thumbs up. If you want to write some words, also happy to receive them. It's going to motivate me to make more workshops. All right, let's take a 3-minute break. All right, the break is over. Let's do another exercise. Right? You have 5.5 minutes. All right, time is up. Interesting problem, right? Functions. Functions are essentially a language that is defined in a certain way. And the most important thing when approaching function exercises is to never underestimate the importance of actually understanding the function. I know that sounds a bit, well, duh, Josh, we have to understand it. But if you can immerse yourself into the function, then answering this will be easy. I'll show you what I mean. So we're told that function x is essentially 2 to the a times 3 to the b times 5 to the c times 7 to the d, when a, b, c, and d represent the thousands, hundreds, tens, and units digit of x, respectively. So it basically means that if x is equal to a, b, c, d, then the function would be 2 to whatever digit is in the thousands times 3 to whatever digit is in the hundreds times 5 to whatever digit is in the tens times 7 to whatever digit is in the units. And immersing ourselves is essentially putting a potential value for x. This will allow you to very efficiently digest the function at hand. So if x were to be 3,846, then the function for x would essentially be 2 to the 3 times 3 to the 8 times 5 to the 4 times 7 to the 6. Awesome. We have a great understanding of the function. Now, we're told that function of z is equal to the function for w divided by 27. Since the function is in terms of prime numbers, of course we want to make this look as similar as possible to the function. So 27 is essentially 3 to the 3. And therefore, we can say that function z is function w times 3 to the minus 3. So let's say, for example, f of w is 2 to the a times 3 to the b times 5 to the c times 7 to the d. Well, that would mean that w has an a in the thousands, b in the hundreds, c in the tens, and d in the units. Now let's make this more tangible, because a, b, c, d are just variables we don't know the value to. Let's say, let's do it like this. Function z is function w times 3 to the minus 3. And we know function w is 2 to the a times 3 to the b times 5 to the c times 7 to the d times 3 to the minus 3. We know we have 3 to the b. So when we have 3 to the b times 3 to the minus 3, it's essentially b minus 3. Great. So if w equals a, b, c, d, then the function for z would be 2 to the a times 3 to the b minus 3 times 5 to the c times 7 to the d. That means that z would have a thousandths digit of a, a hundredths digit of b minus 3, a tens digit of c, and a units digit of d. So now let's make it more tangible. Let's say W is 5,729. That means the function for W is 2 to the 5, 3 to the 7, 5 to the 2, 7 to the 9. Given that we know function z is this times 3 to the minus 3, essentially function z is 2 to the 5 times 3 to the 7 minus 3 times 5 to the 2 times 7 to the 9, which means, yes, that z must be 5,429. The difference between these two numbers, 300. Great. So this exercise can look very intimidating, can look very different from the ones we've been doing prior, but essentially we're solving it in the same way. We're thinking, how can I make my life easy? How can I be organized? How can I understand what's going on? Immerse yourself into the function. How can I make these terms look as similar as possible? When you do those things, then seemingly difficult and complex QR problems become very easy. It is not the math that is difficult. What is difficult is getting to the math you have to do. Now, if you're organized, you can get to that math very efficiently. Great. All right, so I thank you all for attending. If you enjoyed this, please thumbs up and give me a 5-star rating if you so please. Write whatever you feel. This will definitely motivate me to create more awesome workshops for y'all. I'm going to open up mics if anyone has any questions. Thank you, Nam. My pleasure.